Okay, hello. Guess I'm doing this now. Okay, so, hi. I'm assuming that most of you who are watching this are my friends, so you would already know who I am, but if for some random reason this came across your recommended on YouTube, hi, I'm Arson. I'm doing like a crash course thing of Regents Chemistry. If you don't want Regents Chemistry, well, I mean, I guess if you're not from New York, you wouldn't really understand. Pretty much, it's like just normal chemistry. Um, I mean, I did this course mostly for my friends who are taking AP Chem and decided not to take a normal chemistry course beforehand. So, here I am spending hours of my life um, during the summer doing this. I'm kidding. I don't have anything else to do. Yeah, I mean, this is unit one. I mean, obviously, every teacher does it a different way, but I'm just stealing the curriculum from the chem teacher I had. Um, Thanks for that, chem teacher. Appreciate it. I guess let's get into it. Okay, actually, I should probably mention some things. In the description, if I remembered, I hope future me remembers. Um, I will include a link to the Google Classroom, which will have all these PowerPoints that I'll be using in the class, plus the reference table for Regents Chemistry, which it would give if you were to be in New York and take the Regents exam, and the reference table for AP Chem, which I'll probably be referring to a lot. Maybe not the AP Chem one, but probably definitely the Regents one. Um, Obviously, I'll have the PowerPoints if you want to follow along. I suggest you take notes, but obviously that is not mandatory. Again, this is just whatever you want to do. But now I guess we'll get started. Okay, so this is an introduction to chem. This is just a crash course of Unit 1. Introduction to chem. So we're going to be doing 5 things here in this introduction. We're going to be doing the scientific method, which is almost in literally every science course I've probably taken. Sorry, I'm from Earth Science. So, measurements, again, so we're just measuring stuff. Math, it's math. Percent error, just a formula that's on the reference sheet. And then graph, oh, I don't remember what graphing is. Whatever, we'll figure that out together, because I don't remember what's on this PowerPoint. Look at me go, doing great. Okay, so what is science? Okay, science is a way to develop and test explanations of the observations we make, right? These observations will lead to questions, which lead to the experiments to answer those said questions, which is pretty much what just science is, to answer questions made from observations, because we like learning. The scientific method is just an organized way to do this, to approach a question so you can answer it, so you can figure out what the world we live in. I should probably just be reading off this PowerPoint and not saying stuff off the top of my head, but here we are. So this is a scientific method. It's literally the same in every science course you take, but let's go through it anyways. So first, you ask a question. I think you guys know how to do that. Why does fire turn blue when you add this thing? I don't know why that was my first thought. And then you do some research, so you go on Google and you research it. Well, there's more to research than that, but this is not a research class. So, and then you construct a hypothesis, and the if-then sentence. If this happened, then this would happen because whatever, right? And then you test your hypothesis by doing an experiment, and then you analyze your data and come up with a conclusion, like, oh, this is why this happened, and then you report your results. Was that correct? Was my hypothesis correct? And if it wasn't, why? Yeah. And then this is pretty much how you do a controlled experiment. So pretty much you would test for okay, so let's say you're testing for one variable, so that would be the independent variable, which you see here, which is what you're changing, right? Then usually the experimental group is what is, like, let's say you're testing a new drug to see if it's more, like, to see if it works for, like, let's say, nosebleeds, because I get a lot of nosebleeds. That's kind of what I'm known for, in my med group. So, nosebleeds. Let's say you want to test the medicine. If it helps nosebleeds, I don't think such a medicine exists, or I would be taking it, but who knows, right? So you give you have a group of people who have nosebleeds. You give one group the new medicine, you give the control group, so this is the experimental group, the one you give the new medicine to, you give the control group a sugar pill, a placebo, right? And then you measure, like, oh, how many nosebleeds did the experimental group get? How many nosebleeds did the control group get, right? So that's the control results and the experimental results. And then you compare, right? And then if they're the same, pretty much the medicine is useless, doesn't do anything. But if they're different, then maybe the medicine does something, or maybe it makes it worse. Who knows? I don't know, because this is a fake experiment I made up. Anyways, so what is chemistry? Because, this is a chemistry thing, not a course, because I'm not qualified to teach this. So chemistry is the study of properties of matter and the changes it undergoes, and it is known as essential science. Words are hard. Essential science because it overlaps a lot of other sciences. Like next year, I'm taking AP Bio. And guess what the first 2 units in AP Bio are? Chemistry stuff. So at least I know I'll do good on those 2 units. After that, we'll see. Right? I guess that's it. That's chemistry. Anyways, what are chemicals? Chemicals are substances that have same composition and properties wherever found. So water is a chemical, because I have this water bottle that's been sitting here at my desk. Honestly, I don't know how long. Right? Let's say a month, right? But this water is going to be the same as water if I went to India. Yeah. That, because water is probably. Is water a chemical? Give me a second. Classified as a... Yeah, it is. Look at me go. Doing amazing. Okay, let's continue. Okay, so again, water here, where I am right now, in the United States of America, is going to be the same water that I'm going to find in India. Well, after I boil it, because, not risking drinking tap water in India. Just like, my stomach cannot handle that. Okay, I got off topic a lot. Okay, and then a lot of substances are made by chemists, like toothpaste, which is why we have a picture of toothpaste there. It's a combination of chemicals, pretty much. Yeah. Like, fluoride is in toothpaste, I'm pretty sure. Pretty sure. I'm not sure. Not sure, actually. I don't know, I don't make toothpaste for a living. Okay, and then I skipped over a slide. And then these are just some chemicals that are found in toothpaste. Not really important, so. And then again, this is kind of some pictures of chemistry happening. So so the rusting of the copper on the Statue of Liberty is chemistry. I'm pretty sure it's called oxidation. I might be wrong, because I have 2 brain cells and I can't remember anything. The changing of leaves when the seasons change, that's also chemistry. The dissolving of tablets in water is also chemistry. I can't say that word to save my life. Rockets are chemistry. Rockets are pretty goddamn cool. I was gonna curse, but this is going on YouTube, so we're not gonna curse. And nuclear bombs. Not gonna say anything, cause one of you's gonna make a racist joke in the comments. No clue what that is, but chemistry, so cool. And then this is again a normal kitchen, probably. I don't know. I don't leave my room. But yeah, a lot of things around us have something related to chemistry. Like, my lighter's over there to light a candle. I actually have a candle on right now. It smells really nice. Right? And then, okay, whatever. Okay, skip. Anyways, now we're going to be talking about measurements. Wow, so cool. We love measuring stuff. God, dying from cringe just hearing myself talk. Okay, so measurements are used pretty much anywhere. Like, you're going to measure your height, probably, and your weight, or, I don't know, if you're going to get gallons of gasoline to, I don't know, fill up your car. gasoline is really expensive. Honestly, I don't even ask my parents to drive me anymore. I just bike everywhere because those gas prices making me faint. Anyways, thank Lord I don't drive because I would be broke. I already am. Anyway, so pretty much a measurement is it contains a number, so 5 and then a unit, centimeters. You can't just say 5 and you can't just say centimeters. You have to put them together. That's a measurement. Yeah. I mean, I'm pretty sure you guys know what a unit is, but if you don't, a unit is like a physical property that has a certain size. So like a centimeter is this. I don't know how big a centimeter is. I don't have a ruler. Actually, do I? I lied. I do have a ruler on me. Oh my god. So yeah, a centimeter. That big. That's probably the size of my finger. It is the size. Oh, it is the size of my finger now. That's pretty cool. Okay, I'm getting off topic. But yeah, that centimeter not gonna change. And a number, numbers are not gonna. Well, I mean, I guess how the number looks might change because you know, like Arabic numerals. Well, the number meaning is not gonna change. Yeah, and then there's multiple measurements. Oh god, words are hard. There's multiple systems of measurement, known as there's the metric system, which is what's used worldwide, and then we have the imperial system, which the United States uses because the United States are a bunch of idiots who do not like following anybody else. Why do we use the imperial system here? Empiric words, whatever. Why do we use that system here? I don't know, because honestly, it is so goddamn stupid, and I hate it. Like, do I know how many feet are in a mile? No, I don't know how many feet are in a mile. Sorry, that's why I rant about the United States being the United States. If you can't tell, I hate it here, but that's besides the point. But yeah, so in chemistry, we're going to use the international system, which is usually the metric system. Or is that pretty sure it's always a metric system. Whatever. So pretty much, we're probably going to be using these. This is what you would use in, why do they call it the English unit? When I think of English, I think of the British people. I'm sorry. But, pretty much you'll be using kilograms for mass, meters for length, cubic meters for volume, Kelvin for temperature, and joules for energy. Well, you know, we have the metric unit and the English unit. English, whatever. I don't know why you call it that. Right. This is on your chemistry reference table. These are what units are, the symbol, the name, and what it measures pretty much. So, I mean, like, pascals measures pressure, right? And ppm, parts per million, measures concentration, so does molarity. Well, solution concentration, technically, but whatever. Not really, they're not the same thing. You didn't hear that from me. Okay, conversion. So since we're using the metric system, it's really easy to convert between units in the metric system because they're all by factors of 10. So pretty much, let's say you have a meter, depending on the prefix, you know how much you should multiply by or divide by to, so like 1 meter is equal to 10 decimeters. Let's do centimeters because I can pronounce centimeters better. So 1 meter is equal to 100 centimeters because, you know, by using the factors, because centi means, I don't know what centi means, but yeah, since it's 2 raised to the negative 2 power, no, 10 raised to the negative 2 power, then I just multiply by 100 because 10 to the 2 power is 100. I don't think I need to explain math to you. You're not that dumb, and I'm pretty sure you guys know how to use a calculator. I would hope you would know how to use a calculator. Okay, and then again, that's just more conversions. I mean, yeah, pretend that I don't even know why this PowerPoint has the American ones on them because nobody uses them in science. They're stupid. I'm sorry, they really are. I don't know why we use them. They're stupid. But yeah, isn't this? But yeah, these are the base units, quote unquote, where it would be like a meter, and then we would add kilometer or decimeter or centimeter onto it, right? So those are the base units. Yeah. And then again, all base units have a notation of 10 to the 0 power, which is just 1, if you can do the math in your head. I would hope you can. Right? And then these are the selective prefixes. So if you see, I don't know, nanometer, and you're like, I don't know what factor of 10 nanometer is. There it is, -9. So you know what to, divide by and stuff. Yeah. And then this is how to convert from one unit in the metric system to another. So pretty much, like, there's like a ladder, I guess, from. But yeah, so I mean, I don't use the ladder. Since I don't use the ladder, I can't really explain it to you, but pretty much you just multiply or divide by 10 or whatever factor of 10. So if it's like 10 to the second, you would multiply or divide by 100. Yeah. I mean, you can read this if you want. I can't really explain it to you in words very well because I don't use it myself. So, or you can find another YouTube video on it. Sorry, making me do more searching. Apologies, dudes. Anyways. And then, if you guys want to, maybe you can do some practice on this. I'm just gonna wait here. Oh, and also you could use the reference tables for this. I don't think I mentioned that. Oopsie doopsie. Okay, I think that's enough time. And if it's not, it's a YouTube video, just pause it. I don't know what to tell you. Anyways, so 1 is, I can't think right now, 460,000 milligrams. Why? Because milli means 1,000, right? So you just multiply by 1,000, or I'm pretty sure. Actually, I'm gonna take out my reference table just so I can double check. No, yeah, milli is on here, so it's 10 to the -3rd power, right? So pretty much you are going to move the decimal places 3 to the right. I don't know my lefts and rights. It's really embarrassing. And it's on camera too. Even more embarrassing. That's fine. Okay. Well, because you just move it 3 to the right, which gives you 4,000 and 400. You can read the number. Can't speak today. Okay. Next one. 3.12 meters. Why? Because centimeters, centi, 10 to the -2, right? So since you're converting from centimeters to meters, you're going up the metric ladder scale if you're using the method on the previous slide. So you're going to move the decimal places 2 places to the left to get you 3.12. Number 3. 1.002 liters. So 1,002 milliliters is 1.002. Why? So milli is 10 to the -3, as I said in question 1, right? And you're converting to liters. So you go 3 up the metric ladder thing. Don't remember what it's called. Not the point. So that means you move 3 decimal places to the left. I don't know why I made that sound effect. Not the point. And number 4, 100 kilograms is 100,000 grams. Wow, I really don't know my numbers, do I? How you do this? Kilo, 10 to the 3rd power, which is 1,000. So you're moving down the ladder, right? So you're going to move decimal places 3 places to the right. Right, yeah. I'm going to hope I explained that properly, because if I didn't, 21, make you do these. What? Just do them. I'm not going to explain all of them to you. Actually, I feel like I should. You know what? I will. Whatever. Do those, I guess. Okay, cool. Good enough time because I got things to do. That's a lie. No, I don't. Let's pretend I do. Okay, 8.23 meters is 8,230 millimeters. Why? Again, milli means 10 to the negative third power, right? And you're moving down the ladder, so you move the decimal places 3 places to the right. Okay, 1.3 liters is 1,300 milliliters. Why? Milliliters, 10 to the negative 3. You're going down the ladder, you move 3 places to the right. 3.02 grams is 0.00302 302 kilograms. Why? Kilo is 10 to the third, right? From grams to kilograms, you're moving up the ladder, right? So you move the decimal places 3 places to the right. So that is a lot of zeros. God, okay. And then 10.013 grams is 13 oh god, I am exhausted. Okay. 13,000, I don't know what that means. Micrograms. There we go. See, it's on the reference table. Look at me go. Okay, so micro is 10 to the negative 6 power. So from grams to micrograms, you're moving down the ladder. So you're going to move the decimal places 3 places to the right. So 13,000. Okay. Okay, just do these. I don't know what to tell you. Okay, so 0.02. Oh my god, I cannot say numbers. I can't say numbers to save my life. 0.027 centimeters is. I'm not reading out all the zeros. Right. So centimeters. Centi is 10 to the negative 2, right? But then kilometers, whatever, is 10 to the 3, right? So you're moving up the scale 5 times. So you move the decimal place left 5 times. Pretty sure it's 5. I'm gonna double check actually. 1, 2, 3, 4, 5. Yep, 5. Cool. And then 560 micrograms is that many kilograms, right? Why? Micrograms is 10 to the negative 6 power, right? And kilograms is 10 to the, I was about to say negative 3, positive 3 power. So you're moving up the scale 9 times, because 6 plus 3 is 9. So you add 9 zeros. Or no, you move the decimal place to the left 9 times. I lied. So if I'm right, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, just double checking to make sure I did my math right. There you go. Okay. Now, significant figures. Significant figures is in a lot of sciences, but for some reason, chemistry likes to be really strict about it. It was actually on the chemistry regents and I got it wrong, which made me lose 2 points, and I got really mad about it. So, let's not talk about that though. It's okay, we're okay. That was also the only part 2 I got wrong. Are they called part 2s on the chemistry? I don't know what they're called. I don't remember the regents anymore. But besides the point, yeah, I was a little bit mad, but it's okay. Let's talk about significant figures now. I just skipped these because honestly these. Okay, those are just from the worksheet, but I don't have that worksheet, so we're gonna be talking about significant figures, right? So how do I explain significant figures? I don't know. Okay, so pretty much. Oh yeah, actually it's right there on the thing. PowerPoint. Look at me go. So pretty much, significant figures increases the precision and accuracy of taking measurements, right? So let's say you're doing that conversion. If you put it in the calculator, that's the answer that's going to come out. But when you're using significant figures, that's not what you want to use, since it's not really precise and it's not really accurate when it comes to measuring in the real world, right? These are why some measurements can be wrong, because we're obviously human error because we're humans, and humans are not perfect, and if you are perfect, I am very scared of you, because, get away from me, the cross repels you. I'm not even Christian. Don't know why I use that. Anyways, right? And then also, the measuring instrument may not be precise enough. Yeah, look at me go. Yeah, so, precision and accuracy, we don't really need to know these, but precision is the reliability or the reproducibility of a measurement. So can you get the same measurement multiple times, right? And accuracy is how close it is to an accepted value, right? So A, it is both precise and accurate. B, it is precise, but it's not actually, I should probably explain why. Okay, A is precise and accurate because the trash can is like the accepted value. So you get it into the trash can pretty much every single time, and you get it in, which is because you're getting in the trash can, it's accurate. And because you get it every single time, it's precise. B, it is precise because you get it in the same spot every time, but it's not accurate because you're not getting it in the trash can. And then C, it's neither precise or accurate because it's literally just thrown around randomly. You're not getting it in the trash can, and it's kind of scattered all over the place. Oh, well, it's already there, whatever, right? So significant figures, this is pretty much, it's, what, do I have to, screw that. Okay, how do you find the significant figures? Okay, so this is the Atlantic Pacific method, and let me just present. So present and absent, Atlantic Pacific. If you're outside the US, it's probably isn't going to help you. Apologies. Can't do anything about it. Okay. Well, what does absent and present talk about? It talks about a decimal place, right? Actually, it is on the next here. Oh, skip that. So pretty much, you determine if it's absent or present, right? My headphones just came out, right? And then if it is absent, you would start on the Atlantic, absent A, Atlantic A. So you would start on the right. And then if it's present, you would start on the left, right? Then you would find the first non-zero digit. So let's say you have the number 3,200, right? No decimal place, right? So it's absent. So you're going to start on the right. So 3,200, there's two non-zero digits, so you skip over those two non-zero digits and start at the 2 and 3. So yeah, that number has two significant figures. Yeah, and then you count it and every number after it, which I showed you, right? So, do these, I guess. Actually, I'm not just gonna, well, pause the video and do these, because I don't have time to just sit here and not do anything. Okay, number 1 has 4. Why? Okay, so, there is a decimal place present, right? So you start on the Pacific Ocean, which means you start on the left. So we're starting on the left. First non-zero digit, the first digit is non-zero, so you just count 1, 2, 3, 4. Voila. Number 2, 5. That is not lined up, and that's going to bother me a lot. Okay. Okay, so is a decimal place absent or present? It is absent, so you start on the Atlantic side, which is the right. You start on the right, find the first non-zero digit, which is the first one. 1, 2, 3, 4, 5. Number 3, 4. I'm not going to go through the whole Atlantic Pacific thing. So there is a decimal place present, so you start on the left. You skip the first non-zero digit. 1, 2, 3, 4. Number 4, 5. No decimal place. Start on the right. First digit, that's non-zero. The first digit. 1, 2, 3, 4, 5. And number 5, 3. So decimal place is present, so you start here. Skip the first non-zero. 1, 2, 3. Okay. Do these also. So pause the video and do that. Okay. Number 6 is 2. Why? So a decimal place is present. So you start on the left, right? So you skip the non-zero digits. So you skip this one, and then you skip this one, and you get 1, 2. Number 7 is 4. Why? So there is no decimal place present. So you start on the right side. So the first digit is a non-zero digit. So 1, 2, 3, 4. Number 8. 7. Okay, so there is a decimal place present. So you start On the left, first digit is around 0. 1, 2, 3, 4, 5, 6, 7. Number 9. 4. So, there is a decimal place present, so you start on the left side. You skip all the zeros, so you skip these 4 zeros, and these start at the 6th. 1, 2, 3, 4. And number 10 is 1. There is no decimal place, so you start on the right side, you skip these zeros to be left with the singular 1, so one significant figure, right? So, significant figures and calculations. These are more questions on significant figures. I'm not going to go through each of them, but if you want to do it for review, go ahead. Okay, so this is for significant figures are going to be used in addition and subtraction, right? So for addition and subtraction, it's really easy. Actually, you don't really even need to know how significant figures are used, but pretty much, right? If you're adding two numbers, right? So you have these two numbers, right? So each are rounded to different decimal places. The first number is rounded to 2 decimal places, or the hundredths place, and the second one is has no decimal places, right? So what you do, you add them. This is your answer, right? But when you add or subtract using significant figures, you round the answer to the smallest number of decimal places, right? So since this one has 0 and this one has 2, 0 is less than 2, so you would round it to 2 decimal places, right? Or I guess this one is actually rounded to the 10th place, so you would round to the 10th place. Whatever, not important. That's minor. You didn't hear that from me. So, do these. Yeah. Positive. Okay. So this one, you were just going to put it in a calculator pretty much, and then you would round to 2 decimal places because this has only 2 decimal places, this one has 3, so you would use 2. Number 2, round to 2 because this one has 2, this one has 3. 2 is smaller than 3. Number 3, you would round to 1 because this one has 1. And then the rest have more than 1. Number 4, you would do 2 because this one has 2. Number 5, no decimal places because this one has no decimal places. Number 6, 1 decimal place because this one has 1 decimal place. Okay, so now we're going to do significant figures in multiplication and division, right? So how do you do this? First, you see how many significant figures each number has. So this is when the significant figures that the Atlantic-Pacific rule comes in, right? So you find out how many significant figures each number has, right? And then you would round your answer to the nearest number of significant figures, right? So in example 1, 4,560 divided by 14. 4,560 has 3 significant figures, 14 has 2. So when you come up with your answer, you're going to round to 2 significant figures. And you're going to do the same thing with multiplication. 13.1 has 3 significant figures, multiplied by 1.2039 has 5. Then you multiply them, and then you round to 3 significant figures, because that's what the smallest one has. So, pause the video and do these. Okay. There we go. First one, 1.2. You would put in the calculator, obviously, right? And then, this one has 2 significant figures, which is why you round this to 2 significant figures. Number 2, 3,200. This one has 2 significant figures, so the answer is going to have 2 significant figures. Number 3, 3 significant figures, because this one right here, right? So this one has 3 significant figures, so the answer is going to have 3 significant figures. Number 4, 3 significant figures, because, I mean, they both have 3 significant figures, so, you know, yeah, that's nice. And number 5, 2 significant figures, because, this one has 2 significant figures, 1.8. Scientific notation. Scientific notation is also used in a lot of sciences too, because, you know, nobody wants to write out 5 billion zeros, or write out 5 billion decimal places. This is actually, I forgot what his name is, but pretty much this is the number of atoms that are in a mole, so that's pretty cool, I guess. You're gonna learn that a future unit. Um, I don't think there's a thing on how to do yeah, there is a thing how to do scientific notation. Okay, so I'll just explain to you how to use scientific notation. So you have that huge number. I'm not gonna read it out loud because actually I don't even know how to say that number. Um, Pretty much the way you do it is that you make sure the answer, not the answer, but like the thing that's being multiplied, like this number, this base number, I call it the base number. I don't know if that's what it's actually called, but don't ask me. Make sure it only has like one whole number. I think that's what it is called. I'm not very good at English, so apologies if I'm not calling these the right one. And then the rest is decimal places, so 6.02 because this would become your whole number, and then 0.2, you don't need these zeros, and then this is what you would have to multiply to get this number, right? And then this e pretty much just replaces this multiplied 10 to the power of whatever, right? So on a lot of like graphing calculators, they have this e button. I mean, these two mean the same thing. So if you want to use multiplied by 10 to whatever power, you want to use e. Same thing. I prefer e. Yeah, I mean, also these can be used in the negative to represent decimals. So this would be 0. My brain's not braining right now. But yeah, this would just be a decimal instead, right? And then again, this is more scientific notation, more scientific notation. Again, pretty much is just showing you the powers of 10. Pretty much, so if it's multiplied by negative, I mean, again, you can just put it in the calculator, honestly, but, you know, here you are if you need it. And then scientific notation practice. So, pause the video and do them. Okay, so number 1, 3.96 multiplied by 10 to the 2 power. How? Because one whole number, 3.96, and to get this number, you would have to move the decimal places 2 times. You can do it that way, or you can multiply 100, so 10 to the 2 power. Number 2, 1.000 multiplied by 10 to the 2 power. You don't need these extra zeros, but, I mean, they're there for some reason. But, yeah. How? You need only one whole number, right? And then you move the decimal places 2 times to get that whole number, so move the decimal places 2 times to the left to get that whole number, so it's going to be a positive 2. Number 3, 4.3 multiplied by 10 to the negative 2 power. So you need one whole number, so you're going to move the decimal places 2 times to the right, and that's why it's a negative 2. And then number 4, 2.45653 multiplied by 10 to the 5th. Why? Because there's a decimal place here, 1, 2, 3, 4, 5, to get you one whole number, right? And because you moved it to the left, it is to the 5th power. Here are some more. So pause the video and do them. Okay, number 5, 5.3028 multiplied by 10 to the 4th, because you move the decimal place 4 times to the left, so it's multiplied by 10 to the 4th. Number 6, 1.0187. Take the decimal place, multiply it, move it 2 times to the left to get 10 to the 2nd power. 7, 8.2 multiplied by 10 to the 1st power. Decimal place, move 1 time towards the left to get 10 to the 1st power. Number 8, 2.3 multiplied by 10 to the negative 3rd power. Because you take this decimal place, you move it 1, 2, 3 times to the right to get 2.3 multiplied by 10 to the negative 3rd. Here are some of these. So pause the video and do them. This one, decimal place, you just move the decimal places how many times this number says. So 2 times, so 1, 2, 380. So if it's a positive decimal place, you move it to, no, positive exponent, you move it to the right. There we go. Number 2, 20,000, you move the decimal place 4 times to the right. Number 3, 18.9, move the decimal place 1 time towards the right. Number 4, literally the same number, because 10 to the 0 power is 1. So, yeah, or you can just move it 0 times. So, whatever works for it, whatever floats your boat. Here's some more questions, so pause the video and do them. So, this is 0.01902 because it's, so since it's a negative exponent, you move the decimal place to the left. So you move it 2 times to the left to get that number. Number 6, you move the decimal place 5 times to the left to get that number. Not reading that out. Number 7, 0.722, move the decimal place 1 time to the left to get that. And number 8, move the decimal place 3 times to the left. Here's some more if you want to do that. I don't even know why I paused, because you were pausing. Brain damage. Anyways, how would you do this? Where's my calculator? Give me a second. My brain is not braining today. It's not doing the braining today. Hold up, let me. Those are circles. Good to know. Okay, figure out how to do it. Okay. See, look at me, being smart. How do you do these? Because, yeah, I didn't teach you how to do that. Oopsie doopsie. Anyways, the way you do these, or at least the way I do them, after I did some revision in my brain, you take these numbers that are the base numbers, you multiply them, and then you round it to significant figures. So you would round it to 2 significant figures, because this one has 2, right? And then you just add these exponents. So 5, because when you multiply these, you get 4.968. When you round it to 2 significant figures, is 5.0. Multiply 10 to the 5th, because 3 plus 2 is 5. Number 2, 2.4 multiplied 10 to the 7th power. When you multiply these, you get 2.4. 4 plus 3 is 7. Number 3, 4.1 multiplied by 3.7, right? Okay, so the thing is, when you multiply these, you actually get 15.17, but again, as we talked about in scientific notation, you can only have one whole number. So they moved it one time to the left to get 1.5, right? So when you add these, you would get 1, because they moved it again, it's 2. Make sense? I'm hoping that makes sense. I'm really hoping that makes sense. Number 4, 2.86 multiplied by 10 to the 2nd, because when you multiply these two numbers, you get 2.86, and 4 minus 2 is 2. Number 5, 6.3 multiplied by 10 to the 6th. So, pretty much if we were to write this out, it would be 2.5 multiplied by 2.5, which is that, and then it would be 10 to the 3rd multiplied by 10 to the 3rd, which is just 10 to the 6th. Yeah. Or you could just, distribute the exponent. You could also do that, yeah. More scientific notation practice, so pause the video and do it. Okay, number 6 is 2.0 multiplied by 10 to the 2nd, because when you, because this is a division, ooh, fun. So when you divide these, you get 2.0, and then because you're dividing, you would subtract these exponents also, so 4 minus 2 is 2. Number 7, so 6.23 divided by 3.18 is 1.96, and then 5 minus 4 is 1. Okay, number 8, 1.16 multiplied by 10 to the 6th. Okay, so 4.86 divided by 4.16 is 1.16. 2 minus negative 4 is 6. And number 9, 8.22 divided by 3.55 is 2.32, and then 6 minus negative 2 is 8. And the percent error is an equation that you're going to use, which is on your handy dandy reference table. So this is used when you do like an experiment, and let's say the answer you get is like 13 pounds, but when you look, but like a well-known scientist who has so many like credibility in the science area says 15. How off was I? This is when you would use the equation, right? So it determines the accuracy of measurements, right? So pretty much the measured value, you would so what, like, you measured 13 pounds, right? So you would put 13 there minus the 15 pounds. And okay, technically there should be an absolute value sign over here. I don't know why they didn't put that, but it's the absolute value. So it would be 13 minus 15 the absolute value of that, which is 2 over 15, because that's the accepted value again. So 2 over 15 multiplied by 100, which I can't do in my head right now, so it's a number, right? So do this one. Oh, also you're allowed to use your calculator. I don't think I said that. So use your calculator, because I can't do these in my head. Okay, percent error, 9.8. So the measured value is 156, and the actual one is 173. So they would do that, get the absolute value of that, divide that over 173, multiply by 100, equals 9.8. Also, you can just put this part like directly into the calculator, and it'll give you the answer. Especially if you have one of these handy dandy scientific ones, right? These calculators. Never right. That probably has a lot of germs with them. It's fine. And I think that's it. Crash course of Unit 1 of Chemistry. Woo! So if everything goes right, my next video should be up either tomorrow or the day after, and that's going to be a crash course of Unit 2. Ooh, so fun, so jazzy. Well, I mean, I don't know. If this goes right, this video should be uploaded on the 5th. So let's hope this goes right, and that technology doesn't curse me again, because the original video was supposed to go up on Friday, and it didn't. So, technology, please, don't let me down again. Okay, bye-bye, hope to see you next time. Finger guns. Bye.